Welcome to the ICANX Talks. I'm Paul Weiss from UCLA, and I'll be hosting today's lecture. We're delighted and honored to have Professor Jean-Marie Lehn giving today's lecture. And Professor Lehn runs the Laboratory of Supramolecular Chemistry at the Institute of Science and Supramolecular Engineering at the University of Strasbourg. He's a pioneer in supramolecular chemistry, for which he won the 1987 Nobel Prize with Peterson and my colleague Don Cram. He's taken this field further in programming chemistry and motion, as we hear today. In fact, his doctoral student, Jean-Pierre Sauvage, also won a Nobel Prize with my former colleague Fraser Stoddart and with Ben Feringa. He's won innumerable awards, including quite a number of knighthoods. The last time we met was with the incoming president of Botswana, after which we seem to have consumed all of the French ambassador of Botswana's wine. We're in for a special treat today to have Professor Lehn give our ICANX talk, and let me turn the floor over to him now. Professor Lehn.
Thank you very much, Paul. Now I have to split my screen.
I'll stop sharing here.
You see it?
Yes, terrific.
Very good. All right, so I'm pleased to have this occasion to give this ICANX talk. I think this is a very interesting initiative, which is started here. And there have been many talks already, as I saw on the internet. And it's nice to be part of it. I think there will be many people connected. And of course, thanks to this technology, which we have learned to use, thanks, if I may say, to the pandemic. But that's one of the positive things which will come out of it, this using more, this possibility to connect with many people at the same time. So I will try to give you an outline of the chemistry we have been doing, but more of the recent one. It's just a little bit on more older things, but more where we are going, what we have been doing more recently, and where we are going, what are the perspectives. So it will not be strictly supramolecular chemistry, but it will go towards the next steps, which we feel would be important to investigate. So the evolution of visible matter, I insist on visible matter, because in our universe, there's only 5% visible matter. All the 95% is darkness. And we are part of the 5% of visible matter. It started to be divided, particles, which condense together to form atoms and then molecules which become organized. Then at some stage, matter became living, thinking, and maybe there will be something else beyond the complexity of the thinking matter on our planet. And this is the way towards more and more complex states of matter as our universe has generated over 13.7 billion years, as the cosmologists tell us. But, okay, we are sitting on this small planet, and we have science to tell us, to help us to understand what we are doing here. And within the different fields of science, physics, chemistry, biology, let's have a look at chemistry, which builds a bridge between the general laws of physics and their expression in given entities of visible matter, like living organisms. So molecular chemistry starts from building up molecules using atoms. These houses thinking bricks. And beyond that, when molecules get together, they can feel each other, they can interact. That comes supramolecular chemistry, which is a chemistry which might be called beyond the molecule, where three main processes and functions have been studied over the years. How do molecules recognize one another? That is, of course, absolutely fundamental. There is no life without molecular recognition. All our molecules in our body know exactly what to do, when to do, at what rate to do, and so on. So molecular recognition is the basic process of living systems. Reactivity, what do molecules do when they react, transform one another, and how can you carry molecules or entities through a barrier like a membrane, artificial, or a cell membrane. Now, beyond that, once one understands a bit more about molecular recognition and supramolecular chemistry, one can think about systems, molecular systems or supramolecular systems, which by themselves, spontaneously, but in a controlled way, will be able to organize. This can be called self-organization, which can be at equilibrium, which is the one which is right now by far mostly studied, and non-equilibrium, which is very important and which is a next step or a step already also started. And of course, life is a non-equilibrium system. So this self-organization at equilibrium can be considered as a spontaneous assembly of molecular structures and supramolecular architectures where the molecular information is in control. And that is very important. This is a design system where one tries to use molecular information to control the way in which the assembly into organized entities occurs. Just one slide to illustrate this. Self-organization is of that type is by design, because one tries to program the chemical system so that it operates on the basis of the molecular information stored in the molecules and interacting through supramolecular interactions and forces. One example which is simple to illustrate, it's the building up, spontaneous build-up, but controlled build-up of what is called, in a somewhat complicated name, Metallo supramolecular architectures, where the bricks of the architecture are organic ligand molecules, and where the cementing units, the connectors, are metal ions. And on this basis, many very complex structures have been built up, and systems have been set up which generate these supramolecular structures built on metal ion binding. And just a few examples. Very many have been done. Also, Fraser-Stoddart was mentioned earlier by Fraser-Stoddart, Jean-Pierre Sauvage. Many people around the world have used this, and we started in this area in 1984. So we made these helicates, double helices and triple helices, which just for trying to show that it's possible, was a system which self-assembles, forming double helix, triple helix from strands and metal ions. Discrete work molecules, where molecules are held perpendicular to each other, connected by metal ions. In this case, it's silver ions. Then also circular architectures. Here there are 5 ligand molecules, 5 iron ions, and in the center there's a chloride here, just to show this is the one we formed. And then finally, another example, a nanocylinder, which is the result of the spontaneous assembly and the correct positioning of 19 components. You just mix and you get. That's what I mean by design. Things happen on the basis of how they have been designed, and then the program is followed, and the output is the structure you would like to make on the basis of how we have designed it. Now, this is self-organization by design. You try to use molecular information, you program the system, you let it run. You want to control it, of course, through this information, and you can generate functional molecular and supramolecular entities. This, of course, is a very interesting area and is continuing very strongly. However, there's another question I can then ask. What beyond design? That's selection. Beyond design is selection, because here it's the design of a system which will select the pieces it needs to build itself up. The requirements for that are, of course, a diversity of pieces, because the system will have to choose the one which fits best the plan which is being built up, and dynamics, because if the first encounter of two pieces, the collision doesn't lead to the correct object, or the correct meaning thermodynamically, the good one, the correct one, the most stable one, then the object has been able to separate again, to reassociate, and maybe differently. And this reassociation then leads to to mixtures of very many entities which are all in equilibrium. And this is what I call constitutional dynamic chemistry. I mean by that the constitution of the chemical object is dynamic. It can fall apart, it can then reassemble, but on doing so, it can reassemble differently if in the meantime the conditions have changed. So constitutional dynamic chemistry deals with chemical objects which can disassemble, reassemble, and change on doing this process, which means they can adapt. They can respond to forces, agents in the medium. They can adapt, and this is then leading to a chemistry which we call adaptive chemistry, which is now our main line of research. So let's have a look at this. First of all, supramolecular chemistry is by nature dynamic chemistry because the non-covalent interactions are rather labile, so the supramolecular object can dissociate into its constituents, into its molecules, which then can reassemble and can be exchanged. So this is by nature the case. And this is a dynamic non-covalent chemistry by essence. Then, of course, a question can come up. Could we do the same in molecular chemistry, in covalent chemistry? This can be done by importing these dynamics into molecular systems through the introduction of reversible covalent bonds. Reversible covalent bonds are bonds which can break, which can reform, which can change the objects which are linked together. And this is done a dynamic covalent chemistry. And of course, if you want to put these two under the same heading, put them together, then you can call this a constitutional dynamic chemistry, which is both dynamic on the molecular level through reversible bonds and on the non-covalent supramolecular level just to the reliability of the interactions which hold the molecular components together. And that then opens up the possibility to perform adaptation through variation in the constitution in response to whatever happens, for instance, a physical stimulus like heat or pressure, or a chemical effector like adding protons, adding metal ions, adding other molecules, and so on. And this leads then to this area which we like to call adaptive chemistry. Now, what is this good for? Let me just illustrate that. Constitutional dynamic chemistry, what does it do? First, it generates dynamic libraries. In ancient times, would have called that mixtures, untractable mixtures of molecules. Nowadays, because of the progress of the analytical means, they are tractable, and so one generates constitutional dynamic libraries, mixtures of dynamic systems exchanging their parts. That leads to dynamic diversity, and of course makes possible recognition-induced selection, because the recognition between the entities selects some of them so as to lead to the thermodynamically favored object. It has been applied in the search for biologically active substances. It has been implemented to set up dynamic nanodevices and also in material science, polymers, dynamic polymers, and so on. I will give you just one or two examples. I will not talk about dynamic nanodevices, but give you some examples of the others. First, one can notice also that this is a merger of two powerful features. First of all, combinatorics provides the diversity, the reassembly, continuous reassembly of the pieces. And the recognition provides the information, the informatics. So it's a merging of combinatorics and informatics, diversity and recognition, which is of course based on molecular information. Now let's choose one of those reversible reactions, which are important in chemistry, and one of the emblematic one, a very important one because it is valid all throughout organic chemistry and also biological chemistry, the condensation of an amine group, of an amino group with a carbonyl, giving an imine. There are different types of imines, there are different objects which have C and double bonds, but that's the basic type of process, condensing an NH2 with a CO double bond eliminating water and forming the CN double bond. And there are many others, as I said. So what can one do with that? One playing with this object, which is a reversible reaction, and can, of course, be controlled also by pH. This is an important point, but I will not have time to get into that. So what about imine formation? How can one use that for searching for biologically active substances? In other words, applying these ideas to drug discovery. One can start with a set of components which have here, as you see, different shapes, that means different structures, different nature, and they have a functional group, which is this black dot here, which can undergo a reversible reaction. Mixing those components together will automatically generate exchanging constituents, like shown here. We can call that a dynamic combinatorial library, where all the components can exchange and generate all the constituents resulting from the different combinations which they can form. Now, this gives a horrible mess, but what can one do with it? Thermodynamics tell us very easily something. This is Le Chatelier's principle, the law of mass action. Once this is going on and equilibrating all the time, you add a receptor which has a recognition site, and this receptor will preferentially bind with one of the constituents, or maybe more than one, but it will have some kind of a selection process, a search process, which will enable the receptor to shift the library towards the best fitting constituent, meaning that if we want to talk about the lock and key image of Emil Fischer, then we can say that the lock assembles its key. In other words, the system is such that the receptor which you want to sort of to occupy, to which you want to bind something, does the driving. It assembles what fits best. And this has been applied to a number of entities, like, for instance, making enzyme inhibitors. I will show you an example. And then also receptors, substrates, and also receptors for various molecules. And of course, one can call this an adaptation of the dynamic system, this equilibrating system, to the addition of the receptor. The fact that you add the receptor shifts the equilibrium towards an amplification of what fits best, because that is bound and is thermodynamically favored. So let's have a look at one case. The case I want is the first one we have done, but it's quite illustrative. That is why I chose it. Carbonic anhydrase is an enzyme which exchanges CO2 water with carbonic acid. And many studies been done on trying to design, to derive, to make inhibitors of this enzyme, because that's an important feature. So the active site of this enzyme has a zinc ion, as you see here. This is very schematic, of course, and has a hydrophobic wall. And among the many substances which have been studied to be inhibitors, the one I showed you here is a very good inhibitor because it has a KD of 1 nanomolar. It has a sulfonate, a sulfonamide group, which binds to the zinc, the active site. There's a benzyl group, which binds to the hydrophobic wall. And so, okay, this is interesting. And so can we know the answer here, but can we design a system which will find this same answer? In other words, at the beginning, it's better to know the answer to see whether the system can find it. And if we now replace the amide here by an imine, of course, we know very well that an amide is not an imine, then what will happen? So we can set up a constitutional dynamic library with 4 different amines, 3 different aldehydes. 3 times 4 is 12, so you get 12 constituents. One of these 12 has been chosen in such a way that one of the 12 here, the one on the bottom right, is the closest of all 12 to this very good inhibitor, the one which I showed you earlier. So if this is the case, this library should be able to generate, to amplify that constituent on addition of carbonic anhydrase to the set. indeed, if you just look at two constituents among the 12, I have here, I show you the two I present here, this one and this one. They both have this famous sulfonamide, which is important because it binds to the zinc. And they have, this one has a benzylamine group, and here another group. So, in absence of carbonic anhydrase, non-Ca, there is just more or less statistical distribution. And this is a liquid chromatography trace. Now, when you add carbonic anhydrase, what we were hoping to happen does happen. And you see that the one which is closest to the very good inhibitor is very strongly amplified, indicating that indeed there's an adaptation of the system to the binding to the enzyme, a shift towards amplification of that. So that's the proof that the system does what one expects it to do. There are many other cases have been done, and I want just to not to continue on along this line, but I just wanted to illustrate to you what can be done, and it has been done. Now, one question a little bit on the side, as it has been mentioned earlier, Jean-Pierre Sauvage, Fraser Stoddart, and Ben Ferriga, who got the Nobel Prize for molecular motions, we can also here merge molecular motions and constitutional dynamics, the two types of dynamics. Let me shall show you quickly how imine formation, we just have seen. Now, if you have a diamine, like ethylene diamine, this aldehyde, salicyl aldehyde, can bind on one side and issue on the other one. Well, okay, you won't see it. But if you form the monoimine shown here on the right, which is this one here, also on the bottom, then, of course, the CH2 next to that nitrogen and this one will be different. So you will do C2 singles in NMR, and if the imine runs to the other side, this will progressively merge as the motion gets faster. And this is exactly what happens. There is a dynamic covalent motion which occurs through an aminal intermediate. So it's a motion, and one molecule walks on the other one, here only 2 steps, we'll see more. And this is a merging of motional chemistry and constitutional dynamics. Let me just show you, this can be done then in polyamines also, dynamic covalent walking on a molecular track, here on 3 amines, 3 nitrogens. The aldehyde can walk around the system. And of course, as it is here, it is non-directional. But it is a sort of a minimal walker, which is driven by Brownian motion. You don't need to put energy in, of course. It's driven by Brownian motion in aminal steps. It just makes, like when you walk, you take steps, and you walk along. Now you can orient it by making the 2 ends of the track different, so that they have, for instance, different pKa, so that you can use pH to drive one way or the other way. This has been done. So depending on the pH, you can shift the aldehyde group here, which I just schematically represent, to the other side and let it kind of shift it back and forth and forth and back and forth and back and forth as you change the pH. So it's then applicable also to a surface. You can deposit, you can graft amine groups on a surface and then use a particle. It's a bit more complicated, but let me just simplify it. Have a particle which has salicyl aldehyde residues. They can bind, and then if to that surface which contains these amino groups, if you put it into a gradient of pH, then it will go from one side to the other one. When basic, it will have formed imines. When acidic, it will form ammoniums, dissociate imines, so it will drive one way or the other way. It depends, of course, on the pKa's of the nitrogens and so on. I will just illustrate that one can induce motion by stepwise going from one side to another one. So it's a constitutional motion, a constitutional dynamic motion on steps, in this case, on a surface. Now, let's have a look at materials. Constitutional dynamic materials are built on reversible connections. And a specific class of materials, of course, polymers. That's why I use it to illustrate this. We call dynamers dynamic polymers, dynamers. There can be 2 types. First of all, if you take monomers, the components, which have two functional groups, one at each end. And if this yellow functional group is complementary in terms of reactivity to the red one, then you will form a polymer based on a reversible connection. This here can be an imine, for instance. That means you have a reversible connection between two molecular groups, which give a dynamic molecular polymer. On the other hand, if these end groups are not reactive, not chemical reactive groups, but interactive groups, that means recognition groups, then based on the recognition, they will assemble and form here a unit which is now a recognition site. It's formed by molecular recognition between two complementary units. And this leads them to this led to the development of supramolecular polymer chemistry. We started this field in 1990, but I want to illustrate that in a moment, and it has led to something quite interesting. So the first, I give you just the first case which we have studied because it illustrates well what's going on in 1990. We started with a molecule which had at the end of a spacer. The spacer was based on tartaric acid. On end of the spacers, recognition groups built on hydrogen bonding. Donor, acceptor, donor of hydrogen bonding. The complement to that is, of course, ADA. The complement to DAD is acceptor, donor, acceptor. So these two can be synthesized and then mixed together. And what happens? They assemble by forming a triple hydrogen bond between the molecular components so that you form a chain, a supramolecular chain based on the formation of three hydrogen bonds between at each end of the molecules where they get linked together. Note one thing, that already one sees a difference. This is a solid, the starting material here on the left. The starting material on the right is also solid. When you mix it, you get a liquid crystal, which has a very large area of liquid crystallinity, up to 200 degrees and things like that. And this is just electron micrograph to show you that we get nice fibers based on the formation of these chains of supramolecular antitype. That properties which emerge, and I may call that, for instance, the liquid crystalline property is an emerging property from the mixture of the two solids which is to start with. Now that's an interesting system also because it starts with complementary molecular components. They interact to generate a supramolecular polymer chain. Now, this is not the end of it because it was found by light diffusion, light scattering, that the supramolecular polymer chain, in fact, was a triple chain. It was three such chains wrapped around the axis of a cylinder, and the diameter of the cylinder corresponds more or less to the center, one of those dimerities units which bind together. And then you have, I didn't insist on the fact that we have C12H25 chain to make it also nicely soluble. And you have again that it is sort of a helicoidal type of cylinder, a hairy rod, you may call it, which then comes to form fibers. And the one I haven't put here a sign, but the diameter of one of those fibers here is about 40 angstroms, which is what it should be on the basis of the molecular structures. Now it is a three-level assembly from the molecular components to the supramolecular polymer chain, to the triple helical strand, and to the fibrils, which are assembled. And it's sort of a self-organization which bridges scale. It goes from the nanoscale to the micro scale. This is an indication of how successive hierarchical self-organization leads from the nanoscale to the micro scale. Now, the reason why I insisted on the date 1990 was the following. There is, I got in 2013, a mail from a small startup company saying we have used supramolecular polymers, which had introduced in 1990. We may use them to make them biocompatible, And they have then, by this small company called Zeltis, been used to set up materials for cardiovascular implants. Supramolecular polymers, which can be used for the surgical treatment of children which require a cardiac reconstruction. And this has been done. Here is the little girl, Dominica, who in 2013, she has been implanted on October 23rd, 2013, was implanted by Leo Bokeria, Professor Bokeria, who is a famous pediatric surgeon in the Bakulev Center for Cardiovascular Surgery in Moscow. And you see, look, both of them very happy. We were very happy too to see that what we had done simply for basic reasons to try to make supramolecular polymers, a new type of polymers and so on. And here it is done. It took 23 years, but we know very well that when you introduce something into a human body, you have to have a lot of steps to pass. Many children have been many more now than 10. They have also then made pulmonary heart valves, which have been implanted in Budapest, Krakow, Kuala Lumpur, and it's continuing. I cannot tell the very last thing they did, I don't know exactly. But they tell me, the surgeon, for instance, told me it's a breakthrough in surgical practice. Now, another property of supramolecular polymers is that they are self-healing. And here we have a transparent film, very simple components, which leads to a transparent film, very nice polymeric film, which you can cut in two. These are the fingers of my postdoc, Dr. Nabarun Roy, who holds it. Somebody else cuts it. Then you superimpose, you press with your finger, and you can stretch, and it sticks. And this happens within 2-3 minutes. You can pull on it, and it sticks. Now, other people have made self-healing polymers. You can make them on the supramolecular dynamic base, but also on the basis of dynamic covalent chemistry. And this is certainly a field which changes from static polymers to dynamic type of films. Now, let me illustrate what is new with this, what new things one can do with it. Suppose you make now these polymers by taking the dynamic polymers on the molecular level, taking a diamine with a dialdehyde. It gives a polyimine, very simple organic chemistry, nothing special. So if you now make a film which has a given dialdehyde and B, a given diamine, and you get then the film AB, the polyimine. Then you can mix separately another film where you have another dialdehyde, A prime, and another diamine, B prime. And this then gives a film which is A prime, B prime, A prime, B prime, and so on. If you now superimpose these films, and as these connections are supposed to be dynamic, they are imines, then a recombination can occur whereby A can connect with B prime and A prime can connect with B, because in this whole system, there are all possible 4 combinations. 2 are AB and A prime B prime, and the 2 others are A, B prime, and A prime B. So this can then be illustrated. I would have many examples, but let me just take one, which deals using it in a case of optical properties. What about inducing changes in optical properties in this kind of dynamic recombinations? So this is the film AB. Here is the film A prime, B prime. You superimpose here by a corner, and then you let it go. And of course, at the corner, the 2 new combinations can appear by recombination. So A, B prime, and A prime, B. If one of these 2 new combinations has a color or a fluorescence, you will see it. And then my Japanese co-workers at that time made that nice little picture with a cat head. The head and the ears is AB. The inside of the ears, the eyes and the mustache of the cat is A prime, B prime. Then you superimpose, you heat, and you get color and the fluorescence only where they were superimposed, showing that, of course, it works. The recombination works, you generate two new entities, and one of those two new entities has a specific property like color and fluorescence. And of course, that is very general, can be applied to many cases. So it's responsive to, in this case, with heat. You heat it to make it go. Now, let me insist just on one thing, although I cannot cover it, which has to do with biopolymers. Indeed, dynamic biopolymers can also be made, and we have made quite a number of them. We have tried to make one of each category. We have made dynamic nucleic acids, we call DNAs, dynamic nucleic acids, dynamic peptoids, which are not peptides exactly, because you have to introduce a bond which is reversible, like an imine here, and main chain glycodynamers, carbohydrates, modified carbohydrates, where the imine bonds here, the oxime bonds here, you can see, which here form the connections between the basic arabinofuranose type of units here. So we have studied these three cases, but very quickly, I mean, very little has been done. And there is an enormous amount of things to be done. I'm quite convinced that dynamic polymers based on biocomponents can be very interesting in many ways. And for instance, the dynamic peptoids are now being continued and very well implemented by Professor Anna Hirsch. She was in my lab for years, and she's now a professor in Saarbrücken in Germany. And she has done very nice work developing further dynamic peptoids and dynamic proteoids, you may call it. So I would say that really this biodynamics is a field which has many applications, potential applications also, in terms of letting the polymers adjust to, for instance, to skin or whatever you need them for. Of course, I can dream about it, but I'm convinced that there's a lot to be done. Now, what about adaptation? I talked a lot about adaptive chemistry at the beginning. How could one go towards adaptive chemistry? Let me illustrate how adaptive chemistry comes into play. Adaptation can occur through variation in the constitution by selecting different components. And this can happen in response to the environment, change in environment from organic to aqueous, for instance, a phase change, we will see that, a physical effector, heat, pressure, chemical effector, some kind of chemical you add, and even a change in shape. I will only take a few examples. And these form a network, but this is just a notion I want to introduce now, but we'll come back to what I mean here by a network. So, first example I would like to discuss is the following. Here you have two components, molecular components. One of them has two aldehyde groups. The other one has two hydroxides, means NH2s at the end. The center is a very hydrophobic core, and it is fitted with an R, the R here, which is a hexaglyme, a hydrophilic side chain, flexible and hydrophilic. So we have in this molecule something hydrophobic, very hydrophobic, quite rigid, and something flexible and hydrophilic. If you mix those two together, what you expect, of course, we did it, and you get a polymer, a dynamic polymer, which has been studied in detail. It's a sort of a helical rigid rod. Here, I did not represent these hexaglyme side chains, just for clarity. And this is the thing. It's an interesting polymer because it has an inverse temperature dependence. It gets bigger when you heat, whereas you would expect it to get smaller, but it gets bigger. So now this is, okay, the polymer is interesting, but there's an interesting question you can set up for this polymer, this system. You can ask a question. Okay, let's add this. What you get, what I've added here is the same as the carbazole type of unit, except that it has a smaller central core. So that is less hydrophobic than this one. Assuming, which was our assumption, and which was a very reasonable one, that the system will try to thermodynamically minimize contacts between hydrophobic units and water, when you operate in water, then you would say the following. Okay, in aqueous solution, at the beginning, you get what I said earlier, you get this rod. If you now add this, as this is smaller, the central phenyl ring, than the carbazole core, it will just do the same. It will select the units which lead to the smallest contacts between water and the assembling unit. Now, you can say, okay, how do you prove that? One can get a very good argument in favor of that, which is the following. If you transform progressively the aqueous solution to into an organic solution, you should lose the selectivity because it gets more and more organic. So, indeed, on addition of acetonitrile to the aqueous solution of these three units, the aldehyde 1,1,1, adding acetonitrile at the beginning, you have only forming this polymer with the phenyl derivative one staying in solution, whereas when you add acetonitrile, already at about 80% acetonitrile present, you get near random incorporation of both units. You lose your selectivity, which means there's a component selection which leads to the adaptation of the system to the aqueous environment. And when the environment changes, it responds to that, and then it loses its selection. Another case of interest was, can one drive a system by adsorption on a surface? This could be quite interesting, and together with Professor Paolo Samori and his group in our institute, we studied the following system. This is a long chain aldehyde here, and these are three different diamines with 2 carbons, 6 carbons, 12 carbons. In phenyl octane solution, what do you get? NMR shows you that you make only monoimines, very little bisimines at the concentration we were operating at, and you get only monoimines in a statistical mixture of the monoimine of the C2 amine, the C6 amine, and the C12. Now, if you take a drop of this phenyl octane solution and deposit it on a graphite, then what do you see? You get an image which shows you that what has deposited is the bis imine and only of the C12. This is in itself very interesting because what does it mean? It means that adsorption on the surface has driven the reaction to completion, making bis imines rather than monoimines, and it drives the selection only the C12, not the 2, not the 6. So that is a way this shows that in dynamic systems, simple adsorption on a surface can operate a reaction, drive a reaction, and also drive a selection. This is adaptation to surface adsorption, and it's a sort of a self-organization which drives selection, self-organization on the surface. But I could even think further. Of course, this one is an example which proves the case, but one can even sort of dream about something, is that, if a surface can select for given components, then after that they can react. Here, they are dynamic, so they react immediately, and they have this dynamic system, but we can very much imagine that there were systems which by simple deposition would be selected because deposition is better, and then some reactions between these components deposited would occur, for instance, under the sun, heating, and so on. Just sort of dreaming, but I'm quite convinced that surface deposition, recognition by surface deposition can and has a good chance to have contributed to selecting the components. So now I said that I would tell you about networks. And what can I talk about here? All these systems I showed you, these are dynamic interconverting libraries. And of course, each constituent is talking with the other one by exchanging components. And when one exchanges a component, the other ones know about. When one increases, the other ones know about that. They know that means that in terms of available components, they will change. So there will be an interconnection. There will be a network. If we consider the simplest network, where we just have 4 components, I come back to my notation, which I used earlier, the description, AA prime, BB prime, where A and A prime can react with B and B prime to generate what we have already seen, AB prime, A prime B, and A prime B prime. Now, these are 4 constituents. What is the network? A square. These 4 constituents can be put at the corners of a square. And if you now look at the square and at the relationships between the constituents, it's quite informative. On the edges of the square, the constituents which are linked share a component. AB shares A with AB prime, and it shares B with A prime B. So if AB for some reason increases in a closed system, of course, it means that AB prime and A prime B must decrease, because AB can only form at the expense of AB prime and A prime B. So these are antagonists. That is antagonistic connectivity. But now look at the diagonals. It's the opposite. The diagonals link constituents which do not share a component. AB has nothing in common with A prime B prime. AB prime has nothing in common with A prime B. So these are agonists, which means that if AB goes one way, A prime B prime goes the same way. This is very important. These are agonists. I mean by, and it's easy to understand. I mean, it's simple, because if AB increases, it liberates A prime and B prime, which can form A prime B prime. So it's quite obvious that if one constituent increases, its agonist, or sometimes agonists, must increase. I don't just say they increase, they must increase. That's the important thing. So there's an adaptation to physical stimuli, and this is what I call agonist amplification. If AB is the fittest for a given agent, for a given something happening, then it drives amplification of the one which is the unfittest for that same thing. It doesn't mean it's the unfittest for everything, but for the specific agent which drives AB to increase, A prime B prime is the unfittest. And this is quite a general thing, which I will insist on it several times. The fact that in a network, the fittest for a given agent is the unfittest and drives the unfittest for this same object. This can be called adaptive chemical networks. So just a very quick example, very simple, but trivial even. Suppose we have these 4 entities here, these 4 constituents represented here, AB, AB prime, A prime B, and A prime B prime. We now, maybe we mix them, statistical distribution, and we add the middle ion. The middle ion will search, if I may say so, will bind to the best binder, the best ligand. Which is the best ligand? Obviously, NO, this is the ligand, the AB, has the 3 binding sites. In addition, there's an NH which can be ionized. So if you add a little bit of an amine through the binding of the middle ion, you also acidify the NH. The result is that you get a complex shown here, which is the binding of the metal to the best ligand in here. It happens in its ionized form. As a consequence, also the only other thing remaining is the agonist, A prime B prime. So there's a considered amplification, which is driven by the middle cation. We can represent that in the network type of presentation. And if you add the middle ion, you amplify under the action, the binding of the middle, AB, and A prime B prime, which binds much less well the zinc ion, that is zinc. The other 2, which are the antagonists of AB, I have represented them here, but you cannot detect them. There, nothing is left. So it's an adaptation to the addition of middle. Again, I insist, as I said, on agonist amplification. AB the best ligand, the fittest for binding the metal, drives A prime B prime, which is the unfittest as a ligand. So one can also, in that case, also use amplification of the fittest to amplify the unfittest. It's a case where, for instance, A prime B prime could be fluorescent, and you drive it in this way, and so on. And we have done things like that, but I haven't time to get into it. Now, let's have a look at a very important feature, which is that self-organization. That means an increase in organization can lead to a selection. How to show that? It's quite obvious for all of you that a gel is more organized than a solution. That's obvious. A gel is something which is between, let's say, if I may be sort of vague, but between a solution, a sol, and a solid, a crystal or something like that, or an amorphic solid. So, can gelation, the formation of a gel, drive the selection of the component which makes the gel? In other words, a sort of autocatalytic effect. And this has been done here. This was done by one of my Chinese co-workers. She was here. She came from Jilin, in fact. She came from Jilin. So we had found a reaction which is organic organometastasis. I don't want to get into, but this reaction can do the following. This is a derivative of barbiturate. This is an imine, and this imine can exchange its group here, its aldehyde group here, the one with the R, against the one which was on the barbiturate. So you go from this to this, where you exchange the two aldehyde groups here, this one to the other one. This gives then the four constituents, and we know that one of them, in fact, of course, we prepare the system just to demonstrate the effect. One of them forms a gel. This one, where R is a long chain C16H23, this unit there forms a gel. So what happens is the following. You start by making the system, so that's there on the left-hand side. Then you get a gel, and the gel has mainly I here, this unit here, and of course, if it has I, it must have K prime. K prime. Of course, K prime, because it's in the gel, you do not see it by NMR. What you see is what is not in the gel. So I gives you allows you to know how much K prime is around. You can analyze it. So the I is formed, and the I prime is also then, you see, if I forms, I prime must decrease, which it does. As the gel forms, you have a selection of what forms the gel. If you now heat it to the melting point of the gel, 60 degrees, then you get a solution and you go back to the initial distribution. And if you cool back down to 22 degrees and 22 degrees in the NMR spectrometer, you get the same thing. So again, you select, you can, by changing temperature between 20 and 60 degrees, you will come from a solution to the gel. In the gel state, you amplify the gel forming. And in the sol state, you have the statistical distribution. So here, I think this demonstrates something which can be considered as very important, the fact that organization can drive the selection of given components. Component selection under the pressure of self-organization in matter, meaning that the ability to organize leads to the selection of the entities which do organize. This is just representing it by bars. You see, this is the one in the middle here. The K prime is its gel forming unit. It's amplified in the gel state, and at 60 degrees it goes back to statistical. You can even, by the ratio of the ones in the gel and the ones outside the gel, determine that the driving force of the gelation is a ratio of these two, about 1 kilocal. So you amplify again, agonist amplification, the fittest drives amplification, unfittest. You adapt to the formation of an organized phase, a gel, and so the self-organization drives the selection of the components which reinforce the organization It's a self-amplification of organization. Yeah, let's see it again. It's spontaneous amplification of organization by selection of the right components to lead to organization. Now, another person from Jilin did also a very nice piece of work. That is Dr. Guangwen Men. So he did the following. We wanted to extend these things to something more complex than what I just showed. So he studied 3x3 constitutional dynamic network, which means 9 constituents. And let me just bring you through the following way. When you mix these constituents, these components, 3 aldehydes, 3 amines, you get, okay, a mixture, which is a sort of an incomplete network because not all react well. For instance, D4 remains mainly free because that's, of course, an amine or a quinoline, which is not very reactive. So it's not very interesting. I mean, this is just a mixture, just a mixture. But what can you do with this mixture? First of all, if you start by adding copper 1, everything goes to hell. Copper 1 is, of course, susceptible to oxidation. And since copper 2 binds very well to this famous D4 here, this aminoquinoline, in presence of air, just oxygen, what happens is that copper 1 is oxidized to copper 2, which forms then a very good complex with the aminoquinoline, which means the whole network is destroyed. Not interesting. But let's start by adding iron. If we first add iron, you now make the complex which picks up this aminoquinoline between D4 and A6. That's A6 and D4 here. Now, the amplification, the formation of this complex amplifies now a sub-network, the 3x3 network treated with iron 2 leads to the amplification of the iron complex and of the sub-network shown here. Now, if to this you add copper 1, you now have the formation through copper 1 of a complex of the copper 1 with this unit here, D3A7. Yeah, okay, it's for you, it's probably sort of complicated, but let me just say, you then bind copper 1 to this constituent, and as a result, you now amplify this diagonal, which means that in this system, which has altogether 9 constituents, you end up with a highly simplified entity. Just one diagonal of the system is amplified. A first selection with iron leads to the amplification of a sub-network. The agonist is here a network. And then adding of copper 1 leads to this selection of just one diagonal in the network of order 9. Now, this can be done also by adding that. So let me just summarize what happens here. There's a double agonist amplification. The first agonist amplification is the iron with the subnetwork. The second one is the copper with the other, the non-binding. Then it's a conditional response. You can only go this way if you first add iron and then copper. So this system has a sequential structure, and you have to follow a given way. Otherwise, it doesn't work. And finally, important also, is the fact that you increase complexity by adding more entities, but the output becomes simpler and simpler. So there are cases, we have other cases in pure organic chemistry. This is inorganic type of system where an increase in complexity can lead to the simplification by dynamic competition. So from complexity increases, it can generate simplexity. Okay, how much time do I have left? I have still time left. Yeah, still time left.
Yes, please.
Okay, so let's look what happens when you try to submit the system to phase separation. Here we have a mixture of acid and nitrile water chosen because you have an organic solvent and an inorganic and water, and you have lipophilic components which are shown in red, hydrophilic components shown in blue. You mix them together and they then form a reversible covalent bond here. Okay. Now this is what forms at the beginning. Now, because it's a mixture of hydrogen, of acid nitrate and water, if you add something like, for instance, sodium chloride. These are the units. This is the hydro-hydro, the hydro-lipo, lipo-lipo, and lipo-lipo. Okay, these are the four constituents. Now, the distribution you have here, this happens to be the distribution. This you can measure by NMR easily. You can also phase separate by adding an effector. When the phase separates, then you get a distribution such that the lipo-lipo is amplified in the organic phase, and the hydro-hydro is amplified in the aqueous phase. And of course, there are also some combinations, some mixed combinations, hydro-lipo-lipo-hydro, but they are minimal, but they just distribute. So indeed, the result is, when we now look at the percentages, in the organic phase, the one which is strongly amplified is the one here on the right, the lipo-lipo, and in the water phase, the one which is amplified is the hydro-hydro completely on the left. And this bracket just indicates that these mixed ones, they distribute between the two. Now, this means there's an adaptation of the constitutional dynamic library to the phase separation, and we can represent that in the following way. Equilibrium at the beginning. We phase separate, we get a distribution. But you must realize that if the exchange reaction is rather kinetically slow, then at the beginning of the phase separation, what distributes are the same entities as the ones which were present in the mixture. But then you let it equilibrate, and as it equilibrates, you now get at equilibrium a different distribution where the lipo-lipo increases in the organic phase, the hydro-hydro increases in percentage in the hydrophilic phase, in the water aqueous phase, and the other ones just distribute. So then you can reunify the phases by giving, this is something I don't get into, but I can reunify them then. And when you reunify, again, if exchange is slow, at the beginning, you keep the same distributions. And then you let it stand, it equilibrates, and then you go back to the beginning. What I want to show by this is that you generate a kinetically trapped out of equilibrium state, because that is kinetically trapped because the reaction is chosen such as to be slow. And we have now done quite a number of experiments here. We have shown that indeed you can generate kinetically trapped out of equilibrium states, which then eventually you could use to drive something else. And so now let's use also this two-phase system for something else, for generating imprints. I should also say one thing. I will say it here. Okay. Suppose we start here with a phase. This could be the aqueous phase, and this could be organic phase like chloroform, a heavy organic phase like chloroform. You add into this components which generate constituents, and these constituents can react with metal ions. We like metal ions because it's a simple way to demonstrate things. So if you generate this thing here, where you have a given distribution at the beginning, an linear distribution where the constituents and the components distribute between the in phase and the out phase. I call it in phase because that's the one to which we add the initial components. Now we add an effector E1, for instance, a given metal ion. Then this effector added into the in phase will change the distribution of constituents in the in phase. And of course, as a result, it will also change the distribution in the out phase. And you get now what you may call a dynamic fingerprint. The same can happen with E2, another effector, but you get now another distribution. In other words, the addition of one effector number 1 or effector number 2 to the in phase will lead to different distributions in the in phase, but also in the out phase. So if a little Maxwell daemon would be sitting down here in the phase, you would not need to have something going on from the top. You would just, from the changes in distribution, you could deduce from the fingerprint of distribution, the dynamic fingerprint, what has been added in the in phase without going there. I will come back to that in a moment because that's important. So let's have a look at it in terms of a network. As long as your system is homogeneous, everything dissolved, you have a homogeneous solution and you have a square network of the four constituents. From the moment you split the phase, you now have a square prism because you have a network in the organic, in the aqueous phase, and the network in the organic phase. And now the relationships between constituents cross the interface. AB is agonist to A prime B prime, but AB is in one phase, A prime B prime is in the other one. So you really talk from AB to A prime B prime through the interface. And so there's a question, the constituents adapt by component exchange through the interface. There's an agonist amplification between phases, whereas there's agonist repression within the same phase, simply because the relationship is now such that because the agonist of AB goes to the other phase, to the organic phase here, what remains in the aqueous phase, of course, very little. So you have changed the relationships. So you can also say you signal the signal if you do something to the aqueous phase which leads to a change in AB, A prime B prime will feel that change, and so you have a sort of a dynamic redistribution, and this can mean that the information here is in a distribution. You have an adaptation to an effector, and the message of what has been added, which effector has been added to the in phase, is transmitted by a distribution to the other phase without going there. This is quite important because most of the biological transmitters, for instance, acetylcholine at the end between nerves, they have a transmitter which goes there and generates the signal. In this case, it's the distribution which is the information. And this is something a bit ironic because I spent a lot of my life trying to understand molecular recognition, where specific molecules interact in a highly selective fashion. Here, the information is not anymore in a given recognition between molecules, but it is in a given fingerprint in a distribution. Let me finish by the last thing, which deals with the fact that you can also train the systems. You can teach them something. Again, this is just the beginning of something, but I wanted just to show you a proof of principle. Suppose here we have these components that can assemble to lead to these constituents, which are represented here, okay? They define a cavity, a hexagon, a square, and some things between, two between. Okay, now, we start with this mixture, mixing these four components, which generate these four constituents. And we suppose that it is under kinetic control. So we add now a first entity, which is, let's say, a hexagon, which could be, for instance, a metal ion, which wants octahedral coordination, 6 places to interact. And then what does it do? The addition of this effector here progressively, slowly makes the system amplify the one which binds best what you have added, which means this one, the red-green, the AB, the green. The agonist of that is also amplified, the A prime B prime. So this happens kinetically, and so you get this new distribution, which is induced, which is enforced by the addition of the effector. Now, if you add something which removes this effect quickly, then the distribution remains the same because it is kinetically trapped and is not able to go back to the statistical distribution. In other words, you end up with something which is out of equilibrium and which contains the information about what has been added before, so that when you add it again, the recall is very fast. In other words, you start with a system which is at equilibrium, you train it to recognize the hexagon, you remove the hexagon. The training takes time. We know that when we learn something, all of us, we train ourselves, it takes time. But then you remove that, and as soon as you see the object again, you recognize it immediately. You recall it immediately. You can do that also with the square by adding, in this case, it would be, for instance, copper 1. That is what, in fact, what happened. This is iron 2, that is copper 1. And so you can store, you can recall, you can erase by heating, then you get to statistical distributions, and you can retrain by adding something to go from down right to up left, or the other way around. So this at the beginning is the equilibrium state, and these are out of equilibrium states which are memory states. And we all know that the memory of something is an out of equilibrium state. It is something which is not a statistical, because the memory makes a selection among what we remember, what we see, and so on. So this is just the, I don't want to insist more because this is just the actual system. It's published. It's just the actual system which we have used, where we add zinc to train it. You remove the zinc, you recall it again. You add copper 1 to train it this way. You remove it, and you can recall it. You can erase it. You can retrain, and you can retrain, and so on and so on. Okay. So let me just close up by summarizing, especially this more recent stuff which I have been talking about. First of all, we have come to defining constitutional dynamic networks where the constitution of a chemical object forming the network and exchanging components is dynamic. There is a constitutional response to an agent. When you add an agent, the constitution and the relative amounts, the distributions change. Self-organization can drive adaptation. This is, as I said, it's very important. The fact that self-organization drives selects for the components which lead to self-organization. Agonist amplification, the fittest enforces amplification of the unfittest. You can, this is also important, I think, in developmental biology, because in developmental biology, one can imagine cases where when something is fittest, the unfittest is also amplified. Increase in complexity can lead to more simple cases, complexity. The last example was an information processing where you store, recall, and erase, and you can generate out of equilibrium systems. So let me just conclude. From molecular chemistry, we come to supramolecular. It gets organized, better and better organized by self-organization. It must be dynamic so as to be able to adapt and then generate dynamic systems and adaptive systems towards more and more complex forms of matter. All right, I don't know how long I have spoken, but that's the end of it. Thank you for your attention, and I hope I have been clear enough for this presentation. Thank you very much.
Thank you for that brilliant talk. Let me take over the screen here a moment. I think our audience can see what putting together that knowledge across fields and across skills can do in this extraordinary work that you've put together. Now, what I'd like to do is introduce the panelists that we'll have today for discussion. Our panelists will be first Professor Ji Shang, who joined the chemistry department at Jilin University as a lecturer in 1992 and is promoted to be a professor just 2 years later. He moved to Tsinghua University in 2003, and he's now returned to Jilin, where he's the president of the university. He's also the director of the polymer division of the Chinese Chemical Society and executive editor-in-chief of the Chinese Chemical Society journal Chemistry. He's a member of the Chinese Academy, an RSC fellow, an ACS fellow, and his main scientific interests are in interdisciplinary areas of supramolecular chemistry and polymer chemistry, including supramolecular chemotherapy, supramolecular free radicals, and superamphiles. Our next panelist will be Professor Xiaoyu Cow, who got his PhD with our ICANX speaker, Professor Lehn. He held a Marie Curie Fellowship after that, before beginning his academic career at Xiamen University, which just celebrated its centenary earlier this year. He works in molecular and catalytic assembly, supramolecular chemistry, and complex systems. Our third panelist will be Professor Chengwei Kui, who holds a Dean's Chair Professor in Engineering at the National University of Singapore. Among many other awards, he won the Technology Review 35 Under 35 Award for Singapore. He's the editor-in-chief of the journal eLight that we'll hear more about later today. And our challenger will be Dr. Yuqing Sheng, who's a postdoctoral researcher in ICANX lecturer, Professor Jinan Bao's group at Stanford. She got her undergraduate degree and PhD at Beida, where she won a prize for a doctoral thesis. We're now delighted to welcome her as our challenger and our other panelists for a discussion with Professor Lehn. And we should now appear here. And so I think it'll be up to our challenger first, Dr. Sheng, to ask the first question of Professor Lehn.
Yeah, thanks very much for the introduction, and thanks very much for Professor Lehn for the wonderful talk, especially with the first ray of sunshine coming into my room. It's a wonderful morning. And my first question will be that like we've seen from your talk that how nice and how beautiful the supramolecular chemistry is, and how beautiful the concept is, and basically everything that is related to non-covalent interactions can be related to supramolecular chemistry. And you talked about a little about the application of supramolecular chemistry, like in drug discovery. But people occasionally still argue that supramolecular chemistry has more nice concepts than real applications. And how would you comment on that? Thanks.
Has more what? Sorry? Has more?
Has more nice concepts than the real applications. And would you please comment on that?
I don't agree with that for the simple reason that, you know, molecular chemistry has been around all the time. Huh? Since, let's say, since Friedrich Wöhler, when he synthesized urea. Supramolecular chemistry has been around all the time. But it took time to recognize and to be able to study it. So I think there are many applications because, in fact, if I may say you are a supramolecular object. You are based on molecules. All these molecules interact. And okay, I must say, it's not just a concept, it's a reality. And you are the reality. The way you function is supramolecular. No, you see, I don't want to say that supramolecular has solved all the problem. It was always here. But you have to be able to study it. And we now have all the machinery which allows us to look at complex things, at complex mixtures. And all this, we can do things which we couldn't do. And people had already the ideas. For instance, the first supramolecular study, I think, was the people who studied the dimer of acetic acid. The dimer of acetic acid is a supramolecular object. It is formed by two hydrogen bonds. And this is long, this is old, this is 100 years old. Huh? So it was there, but you know, you have a lot of trees. And at some stage, the forest comes up, like behind Paul. The forest is something which comes, you see many trees, and some stage a concept comes up, and then it's okay. Look, I mean, it's a bit artificial. Isolated molecules are molecules. A collection of molecules, supramolecular. Let me give an example, very simple. It's for high school students. A single molecule of water cannot boil, cannot freeze, okay? A glass of water can boil and freeze. What's the difference? The fact that there are many molecules, they interact. So freezing and boiling and refractive index is a supramolecular property. Do you accept that?
Yeah.
Yeah. Dr. Zhang, you get one more question here, and then we'll move along into the panel.
Okay, great. And my second question may be a kind of outlier of this topic, because I'm curious about another rising material, MOF, metal organic framework, that we all know that this material has defined the topological structure, and it has metal nodes, and it has organic ligands connected together. So it sounds like similar as something like cages. So do you think that MOF is another branch of supramolecular chemistry field? And and what's the similarity and difference between MOF and the supramolecular assemblies such as cages in terms of future applications in the near future? Thanks.
I note that you are very interested in applications. I am less.
Yeah.
I think first you have to have the concept, and then the applications come along. But let me think MOFs. When Suzumu Kitagawa gave a talk here, I know him pretty well, and the one thing is, what about making MOFs what about taking the components of two well-characterized MOFs and mixing the whole thing and looking at what comes out? This would then be a dynamic MOFs, of course, in conditions where they are dynamic. And for instance, organic frameworks are dynamic ones, because some people have made also MOFs with imine bonds. So it would be interesting to see what happens and what are, as you say, the applications. And I would even say that if you make the MOF in presence of the thing you want to catch, maybe the MOF will adapt itself to that one. You will make a framework which may have imprinted what is directed by the object you want later on to catch.
Yeah.
Maybe.
Yeah.
It's easy to say, more difficult to do.
Yeah.
That's your business.
Thanks very much.
Let's give Professor Cow a chance to ask his mentor a question now.
Okay. Monsieur Lehn, when I was in your lab, you have been always talking about the chemistry is actually also an information science, and which is also partially related to your talk today. And today now the information science is really knocking the door of every traditional discipline. The artificial intelligence and the data-driven research people are talking around these concepts. And you have foreseen these trends. I think 30 years ago, you already noticed these trends. So I'm curious to know, what's your suggestion to the chemist today towards this coming future?
Look, information is everywhere. I would just say that we are an information system. The development of a human being follows a program, a very, very complicated program. And none of the machineries we have right now is as complex as the development of a living organism. This is extremely complicated. So we have still lots to understand. In fact, I have a quote of John von Neumann. John von Neumann, the famous mathematician. He said, those people who think that mathematics is complicated, they don't realize that life is even much more complicated. Which I think he's right. And coming from him, that says a lot. Okay, now let me say, the system I mentioned at the end, where you have the two faces which separate, and you add an effector on the top. This we studied by looking at we use sort of artificial intelligence way, because it's a sort of a black box, because we don't know really what's coming out. At the beginning, of course, we can, as a chemist, predict if the system is simple enough, we can know that this one binds better than this one. But if you make the system complicated enough, you don't know exactly what comes out. So you let it go, and then from that, you can deduce why it is this and not that. So, okay, I think, of course, artificial intelligence will come into everything. Although, you know, Derek Barton, some of you may know Derek Barton, the Nobel Prize for Conference Analysis. He once said, artificial intelligence is fantastic, but it's even better to have natural intelligence. It's a joke, of course. No, I think, you know, chemical systems, a molecule contains information, obviously. It has a structure, it has a different, it's so obvious that everything is informed. There's information everywhere. And then the reading, let me just, usually for general public lectures, I take simply DNA. DNA has 4 letters. With the 4 letters, you can write all the information for all the living objects, living organisms in our world. And the operation is supramolecular. So the storage is molecular, and the operation, the way they get together, is supramolecular. And you know, with just 4 chemical letters, trivial chemical letters, you can make a tomato or an elephant. That's quite something, no? Of course, there's a lot of developmental biology between, but the basic program is written with 4 letters. It's in some respects, I feel sometimes we have to be very modest. We are the result of 4 letters. Come on.
Thank you.
Very good. Let's give Chengwei a chance.
Hi, good to know you, Professor Lehn. As an optical scientist, I think I have to admit that I don't catch or I don't understand many things that you talk about, but I do appreciate your points of chemistry being very, very complicated. All right, I have a point though. It's amazing to note that in optical analog, we actually did something like optical meta cage, which is related to your previous work using molecules to actually cage another molecules. So my question is, do you foresee any chance or opportunity for light to come into play, for example, to trigger the control of the molecules or to control the cage, meaning sometimes you can open it, sometimes you can close it?
With light, you mean? Using light?
Cage, meaning you can using light to trigger the open and the close of the cage. Whether it is really a possible chance for light to play some role.
Sorry, I don't get it. If it's possible with light to open or close
the cage, because you have did fantastic work on the cage, right? Using molecules to cage another molecules. So,
yeah.
So my question is whether you can use light to, let's say, some infrared light or other light to stimulate or to control this kind of process.
Oh yes, sure, you can. That, for instance, a simple thing is, it has been done. We have done a little bit, but another group has done. When you, with light, you can change the configuration, for instance, from cis to trans or reverse. And of course, when you change that, then of course the whole system, for instance, in one of those dynamic libraries, if you go from cis to trans, you can change the distribution. We have one paper with Lehn Fantôme. You remember her? Xiaoyu, Lehn. She did a system where we had 3 ways. One was middle ion effect. One was nothing, just letting it go. And then it was not selective. Then adding metal ions, it would do one thing. And changing, radiating with light would change the configuration and would do something else. So right. Light can be used to drive the system, so to say.
Maybe I just have a very, very quick non-technical question for you. So now our world is undergoing a great split. So do you have any thoughts on how to counterbalance this trend using chemistry point of view?
The trend in what?
Sorry, maybe my internet is not good. So I want to say that as a chemistry scientist, do you have any comment on how to address this kind of word splitting trend using your own technical know-how? I mean, this is of course a non-technical question. You can skip.
Yes, you said that you also mentioned that the world has changed in the recent times. Yeah. Okay. Is that part of it? Okay. Anyway, if you look at the RNA vaccines, the messenger RNA vaccines, that is chemistry. What did Katalin Karikó and Drew Weissman do? The crux of the matter was to replace a uridine by a pseudo-uridine in the RNA. That made the difference. Of course, people knew that RNA, messenger RNA, would be very important, but it was very sensitive. It was very sensitive to nucleases. It was it stirred up the innate immune system, so that the organism had this very strong reaction. This is the cytokine storm and these things. So the simple chemistry, it's unbelievable in some ways how much chemistry can contribute. Changing the uridine to a pseudo-uridine, a CN bond against a CC bond, that made the difference. So I think, look, as chemists, this is an application. We were asked about applications a moment ago by Dr. Sheng. So this is that's a fantastic application of very simple chemistry, but you have to do it. Look, when I want to illustrate chemistry and convince people that chemistry is an important thing, in fact, I once got the I was once a journalist from a magazine, from a General Public magazine. He said, look, I am writing a paper on the big problems in science. I go to physicists, they tell me, we are studying the basic laws of the universe. Big problem. Okay, sure, big problem. Then I'm going to biologists, we are studying the origin of life. Oh, big problem. What are the chemists doing? They are making molecules, materials, oh, nice stuff, good stuff, but where is the big problem? I told them, maybe the chemists have the biggest problem, because they have to provide the way in which you go from a general laws of the universe to specific expressions of these laws in a given organism, for instance. How do you go from general laws, from the Schrödinger equation, to something like that? How does it develop? What is happening? So that is, I have a slide where on one hand, I have a bridge, where on one side is physics, on the other side is biology, and between is the bridge, chemistry. You have general laws, and of course, we all depend on the laws of physics. That is quite evident. We cannot do anything else than what physics tells us, the laws of the universe. But there are expressions which are different. Like, for instance, when you are a painter, you use the same you use the same colors for very different types of paintings, and so you have all these possibilities. Let's say, another thing I said is that chemistry is to physics what a Beethoven symphony is to the laws of acoustics. And this is chemistry. Chemistry deals with the specific expression of what is happening. And without Einstein, you don't have general relativity. So you have first to understand how Einstein can exist. Okay, I'm pushing it a bit, but I do it on purpose.
Very good.
All right, thank you.
And let's ask President Zhang, it's your turn. You've been very patient.
I enjoy your talk indeed, as always. Let me ask a question beyond your beautiful chemistry. Many professors are eager to have a big funding and big group. It seems to me your research group is not very big, ever from the very beginning. What's your secret to make a big success from a small group?
You know, I understand, depends on the field also. You know, if you're a mathematician, a group can be 2 people or 3 people or maybe 1 person. That's the simplest expression of a group, 1 person. If you are a biologist, or let's say if you are a cosmologist, you have 3,000 people working together, just to do experiments and all that. So it depends on the field very much. So there's no general solution. I think if for a given, I have no direct answer except to say that for a given activity, there is probably an optimal size for a group, which also depends on the person who is supposed to be the conductor of the group, like in an orchestra. Like orchestra is the same. You have a definite number of people. And so, okay, it's difficult. There's no general answer. I'm sorry for that. I have no general answer. But it really depends on the field. And I can understand very well that, especially for applications, you need to you need to get very specific. You want to optimize. And so this may take many more people, much longer. If you want to develop a drug is something rather complex, not the molecule so much, but to find the right one, to study it, go through all the different steps you have to go through. So then there you need a lot of people. This is expensive. But okay, I was usually happy with this. I mean, the largest size I ever had. No, at one stage I had a group which was a little, it was too big, because I had one in Strasbourg and one in Paris at the Collège de France. That was, I think, thinking back at it, it was too much. But I think usually I would say in the field like I am, I think 15, 20 would be a good number. But I have nothing against people who have less or people who have more. There's a different approach. It also depends on how you structure the group. How many people are postdocs? How many people are graduate students? Do you have technicians or not? Do you need technicians? If you are heavy apparatus, you need technicians. That is also part of a group. It's very important. Often one forgets the engineers and the technicians. They are very important. You cannot just keep complicated apparatus operating if you don't have the person who knows how to manage it and how to repair it when it's broken. So I'm sorry, I'm evading your question, but I think it's obvious for you too, I suppose.
Thank you.
Well, thank you so much, and let me thank our panel as well. If we were able to be together now, this is the point at which I would be able to cross the stage and hand you a plaque. And I think one of the most interesting things about the talk today, and every time I've seen your work, has been how the great depth of knowledge in different areas has allowed you to cross scales from chemistry to materials to function. And we're looking for what you continue to do in your research. And I hope that we'll be able to see each other in person, whether it's in Strasbourg or Los Angeles, or perhaps in Senegal at the meeting next December. Thank you so much for I would like
to thank also all of you for this active discussion. And yeah, okay, but you know, all right, it would be much nicer to be all together. But on the other hand, what are the chances to bring together all these people from the West Coast to Europe and to China? Okay, and we have learned something. And you know, I'm sitting in front of the screen. I have forgotten that I am sitting in my office. I see you, I talk with you, and it's okay. It's not the same. We could have a beer together or a good glass of wine, of course.
Yes.
But okay. I will take a glass of
deliver
wine.
my best wishes to your wife.
Very good. And now let me turn over the podium to Professor Alice Zhang.
Okay, thank you very much, Professor Lehn. Yes, really enjoyable talk. And thanks to everyone. Actually, before you leave, Professor Lehn, I still have one question. Yeah, just now we didn't have enough time to ask, but now I have to ask from for the young scientists in front of the audience. Many of them are going to know how your suggestion to the young scientist who is going to be independent in the future in that field. Did you have any comments or suggestions to them?
I mean, about what to do?
Yes, what to do, how to build up the lab.
Yeah, look, I think you heard also already about it. Let me just, I have done many recommendations, but let me just take three, which I think you heard about already. Number one is, don't miss the train. I mean by that if something comes by, you have to notice that it is happening. Don't miss an occasion. And it happened to me many times, where you miss something, you say, oh, damn it, I should have thought about that. But so don't miss the train. When an experiments often want to tell you much more than what you were looking for. Second is, don't jump on a train which is already full. There are very fashionable areas. And many people jump on that. Many people jump on, which is sometimes it's good because, okay, I come back to messenger RNA therapies. That's now a field which will develop. It will be fantastic. We will have anti-cancer vaccines. We'll have lots of stuff. So that is a train which has still to produce a lot. But one has to be very careful when you choose the train which you want to follow. And the third one is think perpendicular, like that. Don't accept what you have been taught all the time without a critical mind. You have to have a critical mind for everything. In most cases, when you do the reverse of what you have been told, it's stupid because what people have taught you is usually correct. But there are occasions where by reversing the way, you get ideas which you didn't have before. So these are three recommendations.
Okay, thank you very much. Yes, I do remember all this because we do the rehearsal and do the interview. But most of the students didn't listen to that. So I have to, ask you to repeat all this. I think that's very important for everyone, Yeah. So especially, especially you don't always jump to the train already full. Right? Yeah, that's really very, very often happened in many young researchers. They always follow some hot topic because the train is full. Remember these words, right? Try to find your own train. Okay. Thank you very much, Professor Lehn. I hope to, host you next time in China or even somewhere, in the world. Yeah, we can join the beer.
I'm waiting for the time to come back to China, but as long as quarantine, I'm not traveling. Yeah, I don't want to sit in a hotel for 2 weeks.
Yes. I think everyone was waiting for the, free time to go together. Okay, thank you all the panelists. Okay. Thank you everyone. Wonderful talk. And today we still have another thing coming out. It's for the E-Light. Yeah, actually today is a wonderful day. So we have a lot of things to do. This was a special moment is for the E-Light. This was a new journal. So today we're going to have this E-Light journal launching talk. Yeah, so we have three important people for this talk. Chen Wei-Chu, already saw him, and Andrew Ozaka was already in the meeting room, and Chen Zi was editor for this journal, so they are waiting to share with us what they're going to do for this E-Light. So first, let me invite Chen Wei-Chu to introduce this E-Light first. Chen Wei, please.
Hi, it's our great pleasure and also privilege to share this great moment, which is about the official launching of our new journal, eLight, which is aiming to enlighten the light. Okay, in the past decades, we all witnessed how optical sciences and engineering of light prospered into a game changer towards the well-being of human society. It reshapes and fuses different disciplines, including physics, chemistry, biology, biomedical sciences. And so optics and photonics research now fundamentally reforms our understanding of the nature. So all these kind of advances motivates us to launch, to start a new journal to timely showcase groundbreaking research in emerging and cross-discipline domains of light. So this eLight journal is in partnership between the CIOMP, the Changchun Institutes of Optics, Fine Mechanics, and the Physics, together with Spring Nature. And it was run by the same team that created the prestigious Journal of Light Science and Applications. So basically, the eLight is coming from the enlighten the light. So we take it in a short form, and also this first letter E stands for a lot of meaningful symbolism terms, like elite, like express, like everything that is good. So basically, we will only report the finest works in optics and photonics. And I think naturally, the audience and the community will have one critical question, that is why we need it. So I will pass it over to our co-editor-in-chief, Professor Erdogan Özkan from UCLA, to elaborate on this. Erdogan, please.
Hi everyone. So can you see me? All right, great. Well, again, hello everyone. Good morning from Los Angeles, and good evening to our colleagues in China and everywhere else. So eLight is really stemming from the success of LSA, Light Science and Applications. And in fact, it's going to be pushed forward by the same editorial team that is behind the success of Light Science and Applications. Perhaps different from LSA, eLight will be quite more selective because it's going to only publish approximately 50 articles a year. So it's going to be quite a bit of selective in terms of how it's going to handle the submitted manuscripts. But this selectivity will be balanced by basically a highly transparent and fair peer review process that's going to be ensured by our editorial board and by our team. At the same time, it's going to be one of the fastest means of disseminating leading results emerging in the broad field of optics and photonics. So if you're a graduate student, if you are running a research lab related to optics and photonics, you may be wondering, how should we make the distinction? When should we submit to eLight? Basically, think of it this way. Within a given year, think of what is the most exciting result that you have achieved over the last 12 months or so. That's probably a good candidate submission to eLight, and we look forward to receiving essentially your finest results coming almost every year. But keep in mind that this is going to be really a selective value, and it's going to maybe publish about 50 papers a year. So to balance this peer review process, as we show in the next slide, please, we have created a highly interdisciplinary and diverse group of professional editors to ensure that your best submissions, your best results in the emerging themes within optics and photonics are peer-reviewed and judged by really leading research scientists who are themselves also conducting some pioneering and great work. So this, I think, going to be a very important part of our success together with you and the community to ensure that we're really selecting the best and the finest every year to be published in eLight. Once again, the powerhouse behind eLight is the same that created the success of LSA, Light Science and Applications. And I'll pass over to Chenzi, who is going to be our leading editorial member, who's going to ensure the peer review process and the communications among all of our editors. Chenzi, would you like to take from here?
Thanks, Adam. Thanks. Indeed, we have a very prestigious and, more importantly, very dedicated editorial board. Besides that, eLight has a professional and well-known in-house editors team, which also created journal Light Science Applications and made ELSA a rapid success as world's leading optics journal and highlighted platform for optical events. Please go back to the previous slide. So here you can see a group photo of us, and you can see that in which Professor Yuhong Bai is the founding director of ELSA, and Wei and I have been working for ELSA since its first year, and Ting Ting and Shai and Jingze have been our strong inputs. So eLight is run by this very strong, experienced, and dynamic editorial team. And you might have also noticed that we have a lot of females here. We are so proud that girl power can take over and stand out here, and we'd like to continue this power and efforts in eLight. So besides that, we have set up global offices from all around the world for eLight. And they are all run by the leading optical scientists from all around the world and their postdocs. That's the reason why ELSA can provide green and expedited channel for urgent papers, and these ad hoc editors in the global offices are also going to help eLight in the same way. So with the cooperation of editorial board, in-house editors, and ad hoc editors, eLight is going to provide the authors a fair, rapid, and a transparent platform for publishing breakthrough findings. So the other benefits for publishing in eLight include waived publication fee until 2022. And once a paper, research paper is published in eLight, we are going to invite scientists to highlight it in Light Science Applications or any other Springer Nature journals to facilitate the transparent and fair peer review. We also provide an option to the authors and reviewers to publish the reviewed reports. Of course, this will only happen under the consensus of authors and reviewers. So the other benefits for publishing in eLight includes, I think it's free and multi-channel news release. Please go to next slide. Thanks. And it's free and multi-channel news release through our channels. Since we have mentioned before, eLight is seeking for breakthrough findings in emerging optics. For such papers, we believe that it's extremely important to make them visible so that your community will learn about and know about your innovative works before they find out any recognitions and common interests. So I'll take two data to illustrate how much eLight values promotion. First, in the past year when we were preparing for eLight, despite, I'm still in the previous slide, thanks. So when we were preparing for eLight, despite the influence of COVID-19, we have presented more than 20 talks in the conferences to promote eLight, and eLight also sponsored Clio Pacific and GuideTech, such huge conferences. And second is that for the inaugural papers, which were just published, we are already planning target promotion in collaboration with Web of Science towards more than 10,000 researchers in optics. So when we go to next slide, I'd like to point out that the editorial team of eLight, we have also been hosting light conferences for more than 10 years, and also a world-renowned event, Rising Stars of Light, and also Light Online Talks since COVID-19. So these events are featured events by UNESCO's International Day of Light. We are utilizing such platforms to help eLight build up their visibility and also help the papers in eLight to build up the visibility. So speaking of papers, I'd like to handle this talk back to Professor Chen-Wei Qiu so that he can talk more about our inaugural papers. Professor Qiu, please. Thanks.
Thanks. So we are very glad and proud to share that we have first two papers published so far in our first issue. So the first one is a perspective paper from Professor Morty Sergey from Technion and Professor Zhigang Chen from Nankai University. So the title is about highlighting photonics, looking into the next generation. I think it provides the authors insightful opinions and thoughts upon integrated photonics, quantum photonics, topological photonics, AI-empowered photonics, and I think it will be very important to get some futuristic advices and inspirations from reading this paper. Then the next paper is from Professor Xinchong Wu from CREO, from UCF. His work is presenting a thorough and in-depth review on the research of liquid crystal and their applications on augmented and virtual reality. And this review covers from all the way from fundamentals to applications. I think it is going to be very useful for not only the experts, but also for the students to pick up from somewhere meaningful. So it basically comes to the end of this promotion and the launching talk. So we would like to thank all the platforms and all the support that we received, including ICANN's perfect platform to let it happen. So just to conclude that this journal will be run by the eLight Press and the eLight editorial team. And me and Adogan will be the co-editors in chief, and Chenzi will be the major managing editors. So she will basically do a lot of jobs, and also the whole team is very collaborative, and also we are very determined to make it successful. And thank you all for your attention.
Okay, Chen-Wei. So before you go to close that, I have a lot of questions for you. Because many audience here, they are very interested and curious about these new journals. So there are a few questions and for each of you, okay? First is, you talk about the fairness a lot. You know, how can eLight guarantee fairness? And can you talk more about your workflow?
This one, basically, I think we talk about statistical fairness. In terms of individual one, I think we cannot really make sure that 100%, because it is also a subjective as well as an objective feeling. So what we try to guarantee for the fairness issue is basically when we receive a paper, so literally we will basically send out to some top-notch scientists in a safe and anonymous way to get their feedbacks, very quick feedbacks. And once it passes a certain threshold, then we will go to the editorial processing, the formal processing, and then the co-editor-in-chief will assign to a suitable or related editorial board member, which is existing now. And even if the paper is very unusual, such that there's no proper or very related editorial board member in our current team, we can also find some ad hoc editors to handle this, to make sure that it will be receiving enough fairness and enough attention and professional dealing of this manuscript. And once everything is running through, then we will basically proceed. Okay, so I think Edgar may add some points to that.
And again, yeah, did you have comments on this?
I think you have highlighted the main points very well. At the end of the day, of course, we'll do our best to be fair and diverse, so that we understand that great science in photonics, in optics, can come from anywhere in the world. So I think one of the most important things that we will be very careful is to make sure that there will be no biases to bigger institutions, bigger research labs. So we would like to make sure that this is a venue for the best work, some of the best work in optics and photonics from various different institutions, from various different countries, various different labs in the world. And I think that's an important message to highlight. We really would like this to be a diverse international effort, and we look forward to receiving the best emerging submissions from various different groups. And the process, of course, will be statistically fair. It's impossible to guarantee to be fair. Any journal will unfortunately fail to sometimes recognize important work, but we would like to ensure that this process is going to be a distributed decision-making with leading people who understand optics and photonics broadly, to ensure that we don't make too many mistakes, hopefully, and even if we make some mistakes, there will be channels of appeal and understand what are the things that we might have missed. So it's going to be a learning experience for everyone, but the biggest power that we have is LSA editorial team has already done, I think, a great job to establish from scratch a very successful journal, Light Science and Applications. So that's a lot of lessons learned, which we will carry on to make sure that this very selective venue, eLight, will be also very successful and at the same time rapid and fair.
Okay, that's really great answers. Actually, I have a following questions for you. And Duncan, you already introduced editorial board, right? You including now is around 30 members from different countries. That's really not a big number, right? If you want to make it really diverse, that's not a big number. How do you plan to manage the manuscript from a current amount of members? Did you want to invite more of them, especially more from China?
So it's a starting point. Certainly, as we increase the number of submissions within the next several months, we will be enlarging our editorial board members and their diversity. At the same time, as Chang Wei mentioned rightfully, we'll be using ad hoc editors as the fields that we receive from sub areas of optics and photonics, as they diversify, would be, of course, seeking out help from other leading experts in those emerging fields as ad hoc editors. I don't see that as a major problem, because as we increase our capacity, have more submissions coming to our editorial office, will accordingly expand into a healthy and diverse group of editors, and at the same time continuously actually seek for finding the right people who might be emerging scholars in our fields to handle the peer review process. So that's going to be a learning experience, and we will evolve into the right size as we become bigger and bigger in terms of the number of submissions that we need to process.
Okay, thank you. Yeah. So the last question is going to Chen Zi. Chen Zi, actually, you are key members of LSA, right? Everyone knows the journal was so successful and very reliable. So how did you do eLight different from other journals? There are many new journals, especially recently, 1 or 2 years. Many new journals come out. Yeah, what are you going to do? Identify yourself and something special. Can you highlight?
Thanks, Alice. Actually, I think the answer to this question is that we are not only different from the other new journals, but also different from the other journals, because that's where the new journal stands. So when we decided to start this journal, actually came from the idea of Professor Austin, Professor Chiu, me, and Professor Bai. So we actually talked a lot about how to make sure this journal is different, and how to make sure this journal is fair and can provide something different and essential for the community. So Ivan and Chengwei talked a lot about this. I just want to add 2 points. First, to guarantee fairness, we actually provide an option to the authors and reviewers. Once both the authors and reviewers agree, we can actually publish the review reports in eLight. So this is not a mandatory option, but this is a option for assisting transparent and fair publication. And also, our topic is quite unique, because if you notice that we are focusing on the emerging topics in optics, because we just came back from Professor Lehn's talk, and Professor Chiu also talked about how to utilize light to manipulate supramoleculars, and also Dr. Zheng talked about how to apply Moyle's lattice and structures in chemistry. So we actually focus a lot about the emerging topics. And I think, as far as I know, I haven't know a journal which is focusing on these new topics. Thanks, Alice.
Okay, that's really, really great. I think today is a wonderful day. It's a big day, especially for the new journal. I hope you have the paper, the latest result and latest ideas published on eLight. And then, yeah, years later is win the Nobel Prize. Yeah, that will be wonderful, start. So I really hope we can celebrate 1 year, anniversary of your eLight next year, this time. Okay, thank you all of you, and good luck to everyone. Good luck to eLight.
Thanks, Alice.
Thank you.
Yeah.
So I can next.
Okay, thanks. Yeah, actually today is the end of the day. I'm going to talk. This week we really have a lot of wonderful things going on, and ICANX is keep on going. And this month we still have 2 speakers on the list. Stephanie Lac will be next week, and Yanyi Huang will be the week in the end of June. And next week is LeCouz from EPFL. He is going to talk about the soft bioelectronic interface. Yeah, it has really, really wonderful, results. I hope everyone, stay with us on ICANX talks, next week. And meanwhile, we start a new event. The new event is ICANX Story. It's every Thursday, 1 day ahead before ICANX talks. This we are going to talk about the stories of the top scientists. So this week is Professor Lehn already passed. So next week will be Professor Paul Wang. You will know how he became so successful and so charming, and a lot of results come out. You come to listen to these talks. This is his stories, and Thursday. And so I see you next time. And I can talks Connect World and Universe. Hope everyone has a wonderful weekend, and see you next week. Bye bye.